students. So in this session we are going to study about radiation. Okay, the topic is radiation. Okay, so radiation, heat energy transfers from one point to another point without any medium, okay, in the form of electromagnetic waves. So in between, if there is any body, okay, it will take some energy and it will emit some energy. Likewise, lot of things will happen. Okay, one by one we will see. Okay, there is absorption, there is reflection, there is transmission. Okay, so one by one we will see. Suppose if we consider a body, okay, first we will concentrate on the receiving part. I mean, a body will be there, a body will be sending radiations outside, just like the sun, and there will be bodies just like earth receiving radiations. So sending part is there, receiving part is there. A body will be acting as sending mode, receiving mode, both will be there. Okay, so everything we will see. First I will explain receiving part. Suppose radiation is coming, a body is receiving, then what all things are there. Okay, so here this is radiation. So okay, so radiation is what actually? Radiation is energy itself. When a radiation is coming from sun, it is energy itself. So I am going to write Q. Okay, so this is the ray that is coming, this is the radiation that is coming, and we are naming it as Q. If this is the body, a part of it based on the nature of the body, okay, some bodies will absorb more, some will reflect more, some will transmit more. It all depends on the body. So a part of it, an amount of radiation will be reflected. So the reflected radiations I am putting as QR. Some will be allowed to transmit. This I am naming as QT. So an amount of radiation is transmitted. And here I am going to write QA. This is the amount of radiation absorbed. Okay, so this is reflected. This one is absorbed. And this is transmitted. Okay, so if a body receives radiation, these three things can happen, or any one can happen, or combination also can happen. Okay, so I could write Q is equal to, that is the amount of radiation that is coming is QR. This is the sum of reflected plus transmitted plus absorbed quantity of energy or radiation. Correct or what? So this radiation is nothing but heat, okay, which is a form of energy in transit, right? So in conduction it was due to molecular vibration. In convection it was actual movement of molecule, but here the energy is transmitting without any medium. Okay, right. So now if I divide with the Q, I can write 1 is equal to QR by Q plus QT by Q plus QA divided by Q. Okay, so this QR by Q, this is called R, and QT by Q is T, and QA by Q is A. Okay, So this R is nothing but reflective power, or we say reflection coefficient. Okay, reflective power or reflective coefficient. See, this is the ratio of energy to energy. So this is dimensionless and unitless. So when we write reflective power, it is not in the sense that this is power, the technical power that we study. Okay, just the terminology, the name is reflective power. Okay, clear? Same way, T is transmittive power or transmission coefficient. Okay, same way, A is absorptive power or absorption coefficient. Okay, note it down. Okay, clear? Shall I erase this? Okay, so A is equal to QA by Q, T is equal to QT by Q, then what? R is equal to QR by Q. So this is called reflective power or reflection coefficient, absorptive power, absorption coefficient, transmittive power, transmission coefficient. Now suppose these radiations will be under different wavelengths. Okay, if one radiation is having some particular wavelength, another radiation will have another wavelength, another frequency. Suppose if we are trying to analyze the absorption coefficient of a particular wavelength, okay, then that is called the spectral absorption coefficient. That is called spectral. All the terms are same, only extra term is spectral. Okay, spectral absorption coefficient. Okay, so spectral absorption coefficient means we put here A lambda, then this will be equal to what? QA lambda divided by Q lambda. So how much of that particular wavelength is absorbed from the total radiation of that particular wavelength? Okay, so here also lambda, here also lambda. So A lambda is equal to QA lambda divided by Q lambda. Same way, spectral transmission coefficient T lambda is equal to QT lambda divided by Q lambda. Same way, spectral reflection coefficient or spectral reflective power is equal to QR lambda divided by Q lambda. Clear? Now this one is of full wavelength, everything putting together. This A is of total wavelength. So what about total absorption coefficient or absorptive power? Is the absorptive power of all the wavelengths together. So this one is actually A is equal to integral from 0 wavelength to lambda A lambda d lambda, we can say. Same way T is equal to integral 0 to lambda T lambda d lambda. Same way R is equal to integral 0 to lambda R lambda d lambda. Okay, so the absorption coefficient is the integration of spectral coefficient, putting the limit 0 to how much till what wavelength we need, that much. Clear? Note it down. Clear? Fine. Shall I erase this? Okay. Now another thing is, suppose A T R. Suppose if A is equal to 1, then T is equal to 0 and R will be equal to 0. So this is a perfect absorber. Okay, we can say perfect absorber. Okay, so best example in this case is ideal black body. Ideal black body. What is a black body? Black body is the body which reflects, which absorbs all the kind of radiations, whatever be its wavelength. Okay, so here we can say black body is the body which absorbs all the radiations falling on it. Okay, so this is a black body. So black body, why is it called black body? Doesn't mean that the body will be black. Best example is sun is a black body. Okay, sun is a black body. Ideal black body, when we say, that is what everything it will absorb, that is an ideal concept. Okay, but 99% is possible. So sun is an example of black body, and there are different materials like that. Okay, lamp black, there is another thing which is near to the idealized condition. Okay, so sun, lamp black, all these are black bodies. So it will absorb the radiations falling on it. Okay, so A is equal to 1 is the ideal condition. Okay, ideal black body. Clear? So this is one point. Another point is, suppose if A is equal to 0, T is equal to 0, then R is equal to 1. This is a good reflector. Good reflector. So always good reflectors will not be a absorber. This will be a bad absorber then. Okay, always good reflector will be bad absorber. I did not say bad transmitter. Why? Because there can be, in practical cases, even if it reflects more, there can be transmission also. But for absorption factor, always this absorption and reflection comes as rivals. Okay, good absorber will be bad reflector also. So good absorber will be always bad reflector. So I can add here bad reflector. Good absorber will be bad reflector. Same way we have A is equal to 0, T is equal to 1, R is equal to 0. Good transmitter. Okay. Clear? Note it down. Okay. See, if you look at something, if it is of red color, that means it is reflecting only a red color, the wavelength associated with the red color. If visible light fall on it, if visible light falls on something, if it absorbs everything but reflecting one particular wavelength, and that wavelength is of red light, then for our eyes we will feel that body is red color. See, this is red. So what is happening here? When visible light falls on it, this is reflecting only red color. Remaining all the things it is absorbing. What about this one? Black. So visible light fall on it, okay, it will absorb everything. It doesn't reflect at all. Same way, suppose a body is blue, okay, it is absorbing everything but reflecting blue. What about white? It reflects everything. It reflects everything. So what happens is, if we absorb more radiation, we will discuss all that, it will increase the temperature of the body. If we absorb radiation, it will increase because heat transfer is there. If we are receiving heat, our temperature will increase. So that is why if we wear black, okay, then it will absorb more heat and naturally we will feel more hot. Okay, so if white, comparatively comfortable. Okay, so that is what is happening here. Okay, so clear? So shall we move to the next thing, next discussion? Okay, so now we need to discuss about emissivity. Okay, or emissive power. Okay, so this is denoted by E. Okay, emissivity or emissive power. Okay, E. So this is nothing but the suppose if we consider a body, that body, it's based on its surface, based on its temperature, it will be emitting some radiations. Okay, sun is emitting a radiation. Same way every body will be emitting some radiations. My body will be emitting some radiation, your body will be emitting some radiation. So based on the surface, okay, based on the surface of the body, okay, it will be emitting. Okay, so what you wear, okay, or if we consider a body, what is its surface? Okay, what is its surface? How much temperature is on there? So likewise it will be emitting. Okay, so here this is nothing but the amount of radiation, okay, emitting per second, okay, per unit time, okay, from this surface. Okay, this is what is emissivity. Okay, suppose if this material has one emissivity, another material will have another emissivity. So that depends on the surface of the material and that depends on the temperature of the material. Okay, so ideal black body, Okay, that is a good absorber. Good absorber means good emitter also. We haven't till now we have discussed about only absorption, transmission and reflection. Now we are moving into emission. So first thing is what we need to understand is good absorber will be good emitter. Okay, and vice versa. Good absorber will be good emitter. Clear or what? So this emissivity or E or emissive power is the property of that substance. Okay, certain things will emit more, certain things will emit less. So if emission is what? Emission of what? Emission of radiation or emission of energy. Only if it has enough energy to emit, then only it will be able to emit. So it should be a good absorber. If it absorbs maximum, then it can emit maximum. If it cannot absorb much, then it cannot emit much. Okay, stock should be there, right? Money comes, money goes. So if enough money comes, we can spend that much. So how much it comes, that much we will have to spend. Same logic here. Okay, so we can say this is nothing but the amount of radiation emitted, okay, per unit time. We can say this is nothing but the amount of radiation, okay, emitted per unit time at a particular temperature. At a particular temperature. Okay, please note it down. Okay, amount of radiation emitted per unit time. One more thing is there, per unit time, per unit surface area. Okay, per unit surface area at a particular temperature. Okay. Amount of radiation emitted per unit time, per unit area at a particular temperature is what? Emissivity or emissive power. Okay, clear? So now this E depends on okay, so this E depends on E depends on the surface of the material, okay. Number 2, the temperature of the material, okay, and we can say nature of the surface. Nature of surface. Okay, so surface of the material means area, then temperature, then nature of the surface. So E depends on these things. Okay, we can I can write here area. Okay, area. Okay, then E is equal to 1, that is maximum emission. Whatever it comes, it will completely emit. Okay, E is equal to 1, complete 100% absorption, 100% emission. Okay, so the E is equal to 1 for ideal black body. Okay, for ideal black body, and E will be greater than 0, less than 1 for gray body. What is gray body? All natural bodies. Okay, anything other than black body we call gray body. Okay, so gray body will have some values for emissivity. So based on that, it will be emitting the radiations. Okay, please note it down. Okay, clear? Okay, so emissivity of an ideal black body is 1, and so even if we take relative emissivity, okay, so that is nothing but the emissivity of the body divided by emissivity of the black body. Again, emissivity of black body is 1. Okay, clear? So hope you understood this. Now based on this emissivity, a body, based on its emissivity value, a body can release radiation. Based on its value, it can absorb radiation. Okay, now spectral emissivity is also there. Spectral emissivity is what? Spectral emissivity is that for a particular wavelength. So this is for that particular wavelength, how much it can absorb. So the amount of radiation, okay, E lambda, okay, amount of radiation okay, absorbed by a body okay, per unit time per unit surface area at a particular temperature. Okay, so till this it was emissivity. Now here we will be adding one more term, at a particular wavelength. Okay, wavelength. Okay, so this is what is spectral emissivity. Okay, so just like we have seen spectral absorption coefficient, spectral transmission coefficient. So here emissivity E is equal to integral 0 to lambda E lambda d lambda. Clear? Students, this is Prevost's theory of heat energy exchange. Prevost's theory of heat energy exchange. So according to Prevost, at every possible temperature, okay, except at 0 degree Kelvin, okay, at every possible temperature there is a continuous heat exchange between a body and its surroundings, and this exchange carry on for infinite time. That is, if there is a body and if it's surrounding, then definitely there is going to be always a heat exchange between that body and surrounding. That is what Prevost's theory of heat exchange. Please note it down. Okay, so here for this heat exchange there are three possible situations. One is, suppose if we consider TB is Shall I erase this? Okay, if you have noted the definition. Okay, so for this heat exchange there are three possibilities. Three possibilities. One is, suppose if TB is temperature of body and if TS is temperature of surroundings. Okay, then so first case is if temperature of body is greater than temperature of surrounding. If the temperature of body is greater than temperature of surrounding, if this is body, okay, body, and around is surrounding, so what will happen? The radiation will be in the outward direction. Okay, net radiation. Okay, net radiation will be from body to surroundings. Okay, if the temperature is more, it will be emitting radiations, net radiation. Okay, there will be incoming radiations also, there will be outgoing radiations also, but if the temperature of the body is more compared to the surrounding, net radiation will be in the outer direction. So what will happen to the body? Okay, there will be cooling effect. Okay, the temperature of body will come down. Temperature of body will come down. Okay, number two, if the temperature of body is less than temperature of the surrounding. If the temperature of the body is less than temperature of the surrounding, what will happen? Net radiation will be towards the body. Net radiation will be towards the body. Net radiation will be towards the body. Clear? Okay, so it's what will happen to the temperature of the body? This will increase. So this is actually heating effect. Okay, so its temperature will increase. The temperature of the body will increase. Clear or what? Third possibility is there. Third possibility is there. Shall I erase this? Third possibility is temperature of the body is equal to temperature of the surrounding. Okay, then absorption of radiation by body, okay, will be equal to emission of radiation by body. Okay, so absorption and emission will happen together. Suppose if this is the body, if one radiation is coming, same amount will be going out. Okay, clear. So here this temperature of the body will be constant, no heating effect, no cooling effect. So this phenomenon happens every time. Okay, some radiation will be emitting from our body, some radiation will be coming to our body, even if the temperature of body and surrounding both are same. Clear or what? Okay. Okay. Next is Kirchhoff's law. Next is Kirchhoff's law. So Kirchhoff's law is nothing but the ratio of spectral absorption coefficient and the ratio and spectral absorption coefficient and spectral emission coefficient will be a constant. Okay, so that is what is Kirchhoff's law. Okay, spectral absorption coefficient, the ratio of spectral absorption coefficient and the ratio of emission coefficient. Okay, this is going to be what? Constant. Okay, say suppose if we consider absorption coefficient A lambda divided by E lambda, this is going to be constant. Clear? Okay. Now, what is this constant value? This constant value is going to be the spectral emission coefficient of an ideal black body. So this can be said like this is going to be E lambda. This is nothing but spectral, okay, emission coefficient of what? Of black body. Okay, clear? So good absorber will be good emitter also. Okay, good absorber will be good emitter, and good emitter will bad absorber will be bad emitter also. Okay, so this is what is Kirchhoff's law. Okay, so we can say, since this is constant, we can say A lambda is proportional to E lambda. Okay. Okay, fine. Next point is Stefan's law. Okay, Stefan's law. Okay, what is Stefan's law is the amount of radiation emitted per unit time per unit area is directly proportional to fourth power of temperature of the body. Okay, amount of radiation, okay, emitted per unit time per unit area, okay, is proportional to fourth power of temperature, okay, fourth power of temperature, let it be there. Temperature of the body we can take, okay, temperature of the body. If surrounding temperature is also given, then we will have to consider that also. Let it be like that. So suppose if I consider amount of radiation as simply E, or this E is nothing but the total radiation per unit time per unit area. So I am going to write this as TA, okay, just for your understanding. And this E is nothing has to do with the emissivity or emissive power. Just for the amount of radiation I have written E, okay. So this is directly proportional to T raised to 4. So this temperature T raised to 4 is nothing but temperature of body, okay. This is what is Stefan's law. And putting the constant of Stefan's law, E is equal to sigma T raised to 4, where sigma is Stefan's constant, okay. Please note it down. Okay, its value, okay, the value of sigma is 5.67 into 10 raised to minus 8, okay, watts per meter square Kelvin raised to 4, okay. So 5.67 into 10 raised to minus 8 watts per meter square Kelvin raised to 4. Okay, so this is a universal constant, okay. Everywhere this is applicable, universal constant, clear? Amount of radiation emitted per unit time per unit area is proportional to fourth power of temperature, clear? Fine. Okay, please pause the screen and note it down. So this is the unit of Stefan's constant. Now what is its dimensional formula? If we see, this is actually Q by TA is equal to sigma T raised to 4. So Q is what? Energy. ml square T raised to minus 2 divided by, this is T and this is going to be again L square. So this is equal to what? Sigma, and this is T raised to 4 theta raised to 4. So L square can be cancelled, this will go up, m T raised to minus 3 theta raised to minus 4. This is the dimensional formula of sigma, okay. Clear? Now when we get problems from this area, how to deal this, okay. So the amount of radiation emitted per unit time per unit area is asked. Then it is clear. Suppose Q by the amount of radiation emitted per unit time per unit area is asked. What we will do? We will do E is equal to sigma T raised to 4 we will do. Next thing is, so here that surrounding temperature is not given, okay. If surrounding temperature is not given, then they are asking the amount of radiation emitted. There is no mention about a net radiation and all, okay. Fine. Now suppose if they ask heat itself, how much amount of heat is emitted from a body of so and so area for this much duration of time, then what we will have to do? Then we will have to do Q is equal to sigma T raised to 4 into T into A. So here T is time, A is area of the body, okay, and T is temperature of body. Clear? Okay. Now suppose if the body is not ideal black body, ideal black body is emissivity will be maximum. So E, small e, emissivity or emissive power is going to be 1 for ideal black body. So we can say for ideal black body, Q is equal to sigma T raised to 4 T into A, 5. For gray body, for a gray body of emissivity 0.8, 0.7, some value is given, then we will have to consider that also. Then the amount of radiation, okay, emitted from the body is going to be sigma T raised to 4 T A. So here we will have to multiply with the E also. This is the emissivity of the body. Okay, if the body cannot emit full, okay, it has got some emissivity, only that much it will be absorbing, that only that much it can emit. So for an ideal black body, E is equal to 1, no worries. For a gray body means any body other than black body, Q is equal to E sigma T raised to 4 T into A. So this time this is the amount of radiation emitted from a body of area so and so for a time duration T is equal to say 5 seconds or 10 seconds. Clear? Now suppose the same formula, okay, will take the form if surrounding temperature is also given. So Q is equal to E sigma TA. Okay, so here temperature of the body is also given, same way temperature of the surrounding is also given. Okay, so that also we will have to consider. Okay, clear? Note it down. So this is temperature of the surrounding, this is temperature of the body. So here we can say this is nothing but net loss of radiation. Net loss of radiation. Okay, why we have done like this? Suppose if a body is there, so from this body this outgoing radiations are there. What is this actually? This outgoing radiations, suppose if you mark with the blue ink, okay, these are outside outgoing radiations. So this outgoing radiations we are writing E TA sigma T raised to T of the body raised to 4. Now say suppose incoming radiation is also there, incoming is also there, both will be there. Okay, both will be there, but if there always outgoing and incoming radiations will be there, but if the temperature of the body is greater than the surrounding, outgoing will be more. If the temperature of the body is less than the surrounding, incoming will be more. That is what. So this is going to be what? E T A sigma Ts raised to 4. So if the outgoing we are taking as plus, then at least this we will have to take it as minus. So if we subtract this, if we take the things outside, only this will be there in the bracket. Clear? That is all. Clear? Fine. Okay, so amount of radiation per unit time, per unit area, then we can say what? E is equal to sigma T raised to 4. Okay, so E is equal to sigma T raised to 4 I said. Now suppose if they ask rate of, okay, rate of emission. Rate of emission, okay, total emission is how much? Total emission will be Q is equal to E sigma T raised to 4 into T into area. Now rate of emission is going to be, we can divide this Q with the T. So Q by T is equal to what? E sigma T raised to 4 into area A. Clear? Okay, this is the rate of emission of radiation. Okay, rate of emission of radiation is this. Okay, please note it down. Q by T, nothing else. Hi students, so here we are going to see the rate of cooling. Rate of cooling. What about the radiation emitted from a surface? So radiation emitted from a surface is its emissivity of that surface, Stephan's constant. How much is the area, that much will be the emission. Then how long, how much time, that much time the emission will be there, into the temperature of the body raised to 4 minus temperature of the surrounding raised to 4. Okay, so when the heat is radiated, what is happening? Heat is released. We have studied in calorimetry, when we take ice, if heat is heat is liberated from ice, heat is released from ice, what will happen? The temperature of the ice will decrease. If heat is liberated, steam will become water. If heat is liberated, the temperature of water will come down. When heat is liberated, water will become ice. When heat is again released, ice will become ice of less temperature. So can I write here MC delta TB, that is the change in temperature of the body. Okay, when how much is released, what is happening here? Change in temperature will happen, correct? So this is equal to E sigma A into time, temperature of the body raised to 4 minus temperature of the surrounding raised to 4. So sometimes in text, instead of temperature of surrounding, they may give temperature of surrounding as T0, temperature of the body as T. Okay, for your understanding I am writing B and S. Okay, so now the rate of cooling, is nothing but the speed of decrease in temperature. Rate of cooling is how fast it is getting cold. So rate of cooling, so delta TB is the decrease in the temperature of the body. We can bring this T here. This is nothing but rate of cooling. Now we will bring all those terms the other side. We will be getting E sigma A divided by MC and temperature of the body raised to 4 minus temperature of the surrounding raised to 4. So this is what is the rate of cooling. Okay, so using Stephan's laws, okay, using Stephan's law, we can write temperature, the rate of cooling also. Note it down. Okay, so the rate of cooling depends on what? Rate of cooling depends on, number one, nature of surface, nature of surface. From where we are getting this? Directly proportional to, actually, okay, directly proportional to nature of surface, that we are getting from emissivity E. Okay, so if the emissivity is more, the heat will be liberated fast, rate of cooling also will be more. Number two is what? Area. Best example is, if you maybe you might be remembering, your mom gave you a cup of milk. If it is hot, when we were small, we will be reluctant to drink. So what they used to do, they pour that milk in a plate and they will move like this. Immediately fast, okay, cooling will happen, and again will pour in the glass and will give. So what mom has done, she pour in the plate, she increased the area, the rate of cooling is increased. So area, this one. Now another thing is what? The temperature difference. Either the temperature difference between body and surrounding must be more, or simply we can say, or otherwise temperature of body is more, then again rate of cooling will be more. Clear? Fine. Fourth point is what? Okay, shall I erase this part? These are all direct proportion. Okay, these are all directly proportional. Fourth point is mass. Okay, mass. Fifth point is specific heat capacity. Specific heat capacity of the body. Mass of the body, specific heat capacity of the body. Okay, so these many factors are there. Cooling depends on, all these are directly proportional, this is inversely proportional. Mass and specific heat capacity. This is constant, Stefan's constant, right? So if material changes, C will change. But even if we change the material, sigma will not change, that is universal constant. Clear? Shall I erase this? Okay. Okay, so what we have seen is rate of cooling. Now Newton's law is also there. Newton's law of cooling is also there. Okay, so that also we will study. Okay, so what Newton has said is for very less range of temperature change, if Newton's law cannot be applied if the temperature change is very large. For small range of temperature change, say for example maximum of around 35 degrees Celsius, Newton's law of cooling, okay, Newton's law of cooling can be applied. So what he says is the rate of cooling is directly proportional to the temperature difference between the body and the surrounding. Okay, that is what Newton said. small temperature difference. Small temperature difference, okay. Rate of cooling is directly proportional to the temperature difference between body and the surroundings. Okay, note it down. Okay, so for if the temperature between the body and surrounding is more, then Newton's law of cooling cannot be applied. Okay, so for if it is less, then Newton's law of cooling can be applied. So what he says is dt by dt. Okay, so change in temperature by change in time. Okay, dt by t. So here, since this temperature is decreasing, okay, we will put a minus, is proportional to temperature of the body minus T naught. Okay, I am writing this as T minus T naught. Okay, using here, this is temperature of the body, this is temperature of the surrounding. Okay, dt by dt. Okay, now if we put a constant here, dt by dt is equal to k into T minus T naught, k into T minus T naught. Now if I bring this here, this will become dt by T minus T naught is equal to constant, this dt will go here. Okay, fine. Now we will integrate. Okay, so for a small duration of time dt, the temperature difference is this dt. Okay, so for a time duration t we need to find, so we will integrate this. So when we integrate, okay, so integrating dt by T minus T naught, this is equal to, again minus we will put here, integrate k dt. So when you integrate this, we will be getting natural logarithm of T minus T naught, T minus T naught, this is equal to minus k into T plus a constant, plus a constant. Now in order to remove even if we write a constant here, that constant will be sent to that side, again that also will become constant. Okay, so now in order to remove natural logarithm, we will be doing T minus T naught. This side what we will do, e raised to minus kt plus c. So T minus T naught is equal to e raised to minus kt into e raised to c. Can we write like this? So this will become a constant. So T minus T naught is equal to, again, a constant into e raised to minus k into t. So this T minus T naught is equal to k into e raised to minus kt. Okay, remember this relation. Okay, note it down. Remember this relation. Okay, then this one also. Okay, now I am erasing this. Okay, so using these two relations, two graphs are given in NCERT. Okay, so first one we will do this, t minus t naught. Okay, and here if it is t, okay, time, then how to plot this? E raised to minus kt. Okay, so this is how the graph is going to be. T minus t naught is equal to e raised t minus t naught is equal to e raised to minus kt. This is how the graph is going to be. So here t minus t naught is in y-axis and time is in x-axis. Now here if we put natural logarithm of t minus t naught, this is in the form of y is equal to mx plus c. Minus k is the slope. Minus k is the slope. So we will draw a straight line with the slope minus k. Okay, note it down. Okay, clear? See students, for solving numerical problems on Newton's law of cooling, you can use this formula. So if this is the initial temperature of the body and this is the final temperature of the body, this change is happening in a time span of small t. So this is the change in temperature and this is the time. So this is the rate of cooling, initial temperature minus final temperature by T. This is equal to constant into the change in the difference in the temperature of the body and the surrounding. So the average excess of temperature is T1 plus T2 by 2 minus the surrounding temperature. So using this formula we can find the rate of cooling, we can find the initial temperature, final temperature. So remember this formula. Using this formula we can solve problems on Newton's law of cooling. Please note it down. Now let us look into another piece of information. So here just we will analyze this graph. So in this graph, suppose initially if we maintain a temperature T1, okay, so when you maintain a temperature T1, obviously a body will be emitting its radiation, and when a body emits radiation, there will be radiation of different wavelengths. Suppose when we keep a body, that body will experience different radiation, they will absorb it. So when it absorbs, it may have different radiations and that will have different wavelengths also. Okay, so obviously when it emits, wavelength radiations of different wavelengths also will be emitted. Okay, so that is the criteria which we need to understand. Okay, bodies emit radiations of the different wavelengths. Okay, emitting. So when we maintain a temperature T1, obviously that body is emitting radiations of different wavelengths. So in y-axis it is the intensity of the radiation. Okay, intensity of the radiation. Okay, spectral radiation intensity means if these are different wavelengths, okay, here what is the intensity for each wavelength. Okay, now when we look at this one at T1, one radiation, okay, or radiation of a particular wavelength is maximum. Okay, so its intensity we have written like a E lambda m1. This lambda m1, m means maximum, this m stands for maximum. It doesn't mean that this is the maximum wavelength. Lambda m means the wavelength at which intensity will be maximum. Okay, see, if this is lambda m1, here another wavelengths are there, and right side also another wavelengths are there. So maximum wavelength will be coming in this direction, right? So this lambda m1 doesn't mean that it is maximum wavelength, but lambda m is nothing but the wavelength where the maximum spectral radiation intensity is there at that particular temperature. So at T1 we are getting the maximum intensity for the wavelength lambda m1. Okay, now suppose if I am increasing the temperature, so when you increase the temperature, again that body will be emitting radiations. So this time I am getting maximum. When I increased the temperature, I am getting the maximum intensity of radiation at a wavelength lesser than this. Temperature is increased, wavelength is decreased. So here we are getting the maximum spectral intensity. Now again increase the temperature, this wavelength shifted back. Okay, so this is the behavior. Okay, so maximum intensity we will be getting at a particular wavelength for a particular temperature. Again, if we change the temperature, okay, if we increase the temperature, wavelength will be decreased. What wavelength? Wavelength where the maximum intensity is available. Now if we increase the temperature further, again wavelength will go down. Wavelength will go down in the sense we will be getting the maximum intensity at a lesser wavelength. Likewise, if we decrease the temperature, wavelength will increase. Now what is Wien's displacement law? Wien's displacement law states that the wavelength where we are getting the maximum intensity into that particular temperature will be a constant. Okay, into that particular temperature will be a constant. So suppose we can write like this: lambda m1 T1 is equal to lambda m2 T2. Okay, likewise, so this is a constant. That constant's value is what? B is equal to 2.89 into 10 raised to minus 3 mk. Okay, so this is the unit and this is Wien's constant. Wien's constant. Clear? Suppose if we know the wavelength of a radiation, then using this constant we will be able to find the temperature of that source. Suppose sun rays is coming, which in wavelength has got maximum intensity for sun's radiation, that into this T will be the temperature in sun equal to what? Wien's constant. Likewise, we will be able to find the temperature of far objects. Okay, so this is what is Wien's displacement law. Okay, please note it down. Okay, students, so these are the basic understanding, basics or fundamentals of heat transfer also. So with that, all the fundamentals or basics and or the theory part of thermal properties of matter is done. Now we need to practice problems on this. Okay students, thank you, goodbye, good luck.